So our next speaker is Dreyer from the Max Planck Institute for Software Systems. Derek is known for his expertise in Scottish whiskey and also in type systems for functional programming languages, in verifying compilers, in verifying concurrent programs, in dealing with weak memory models. And so recently he has started working on providing formal foundations for the Rust programming language within an ERC project that he's leading. And also one of the latest news is that he has won the ACM SIG Plan Robin Milner Junior Researcher Award, which is a great achievement. So congratulations and welcome.
Thank you, Peter, for that lovely introduction. So can everyone hear me? Yes, good. Today I'm going to talk about the RustBelt project, which is this project that we started technically last April, but it's really started in 2015. And I'm pretty excited about this work because it's sort of a rare opportunity for us to look at a real practical programming language problem that affects a lot of people and attack it using the kind of techniques that we've been building, not just we, but that the whole program verification and semantics community has been building up over the past 20 years. And it's something where I think you really need those techniques in order to make progress on this problem. And at the same time, by looking at this real language, namely Rust, it's serving as a stress test for these techniques and forcing us to innovate and really push the technology further than it has gone before. So what I'm going to talk about today is the first work. We've had a number of papers in the project, but this is the first work, the first paper on Rust itself. And it's joint work with Ralph Jung, who's my student, Jacques-Henri Jordan, who was my postdoc. He just started at CNRS this month, and Robert Krebers at TU Delft. How many of you have heard of Rust? Okay, good. How many have actually programmed in Rust? Oh, okay, all right. So it's actually more than I expected. So in any case, don't worry if you don't know anything about Rust really, because I'm going to go in the first part of the talk. I'm going to go through a sort of brief tutorial about the interesting parts of Rust from the point of view of these sort of foundational questions we're looking at here. So what is Rust? Okay, so Rust is a language that has been developed by Mozilla officially, I guess, since around 2010. And it's intended as a kind of safe systems programming language, sort of a safe alternative to C or C++. It has a kind of interesting combination of, you might say, the modern goodies of languages like ML and Haskell, so things like first-class functions, polymorphism, traits, which are like Haskell type classes with associated types. But in addition, it gives you low-level control over resource management, memory allocation, and data layout in the style of C++. The key sort of distinguishing feature of Rust compared to many previous approaches is that it is a sound type system with pretty strong guarantees. So it guarantees sort of the usual type and memory safety, but also data race freedom. I put that in bold because actually that's the question we're studying in this project is that actually the case? So is Rust actually sound? And what would you need to do to demonstrate that? Because that really is the selling point of Rust. I mean, there's various nice aspects of the programming language design, but really the main selling point is the soundness guarantee, and that's really quite, as I'll explain in a minute, that's really quite up in the air. The high-level goal of the RustBelt project is to build foundations that will allow us to actually prove the soundness of the Rust type system, and in particular, because it turns out that things get quite technically involved, we want to do this in a machine-checked way, and we're doing this all completely in the Coq proof assistant. So that's the very high-level goal. Before I go into, basically the talk will have two parts. I'll show you some stuff about Rust. I'll give you a little introduction to the interesting features there, and then I'll talk about RustBelt and what we're doing. But I want to just highlight the key challenge up front. So the key challenge from my perspective is that sort of the way that the language is often sold is not what's actually going on. So often when you hear talks about Rust, and this is for a sort of first approximation, this is a reasonable way of presenting things, you hear the slogan that there's no mutation through aliased pointers. So there's the idea being that the language has various mechanisms for allowing you to work with, to mutate things and to alias things, but you can't have mutation and aliasing at the same time. That's sort of the whole idea behind Rust is mutation plus aliasing is the root of all evil in the sense of causing various anomalous behavior. And indeed, the type system at a superficial level, and you'll see in a minute what I mean, does seem to give you that property. However, this is completely false. So many Rust libraries, including very important Rust libraries, do permit mutation through alias pointers. That's in fact their whole reason for existence, because sometimes you need to mutate through alias pointers. So they're there for a reason. And the safety of these libraries in conjunction with the core type system of the language is highly non-obvious. In particular, precisely because these libraries do permit mutation through alias pointers, they cannot be implemented inside the core type system of the language, which indeed prohibits mutation through alias pointers. So they have to go and make use of unsafe features. And the question is then, why is it safe to mix these libraries with sort of safe, well-typed Rust code? And that's the big question that we're studying here. Sort of the root question is why is this combination sound? Okay. And by the way, during the talk, please feel free to ask questions especially during the overview of Rust, because if you don't understand sort of what's going on in the language, then the way we're modeling it will make no sense at all. Okay, so the core idea in Rust is this concept of ownership. Okay, and this is not a new concept, by the way. A lot of the stuff that's going on in Rust is derivative of a lot of work on, especially on academic programming languages, and work on ownership types and substructural type systems, linear type systems. I'm not going to list all the many efforts in that direction, but a lot of these ideas you'll find them familiar from the literature. So ownership, the idea is that when you have access to a variable in Rust, it's not just some value. Okay, it actually represents privileges to, for example, mutate the variable. The way that this is talked about in the Rust world is through this concept of ownership. So I'll illustrate that with this simple example. The idea here is we have two threads. So this join is just spawning two threads in parallel. This is the first one. That's the second one. And they're just at the beginning we set up a channel that's going to be used to communicate between the two threads. So at the first line, does this work? Oh, yeah. We create a sender and a receiver end to the channel, okay? And the idea is that the first thread is going to get ownership of the sender end, and the second thread will get ownership of the receiver end. And here that just sort of happens automatically by the Rust type checker figures out that the first thread needs to refer to the sender, and the second thread needs to refer to the receiver here. So it just transfers, and because you use the move keyword, it automatically transfers ownership into those two threads. And then what happens here in this example is really simple. It's just some heap allocated pointer B is created. It's assigned to 1, and then ownership of B is transferred from the first thread to the second thread by calling send on B. And then the second thread receives B, and then it reads the contents of the pointer. Okay, nothing too complicated. So this code type checks. Okay, let's see an example of something that would not type check. So for example, after I've sent B in the first thread, suppose I try to mutate B through. Suppose I try to mutate it through the pointer. Rust will give you an error saying that you've lost ownership of B because at this line where this was where it was transferred through the channel. This is crucial because if this were allowed to type check, it would mean you would have the potential of a data race, right? This thread could be modifying B at exactly the same time that this thread was reading it, and they're not using any synchronization. Okay. So this could have sort of undefined behavior. And in terms of ownership, this makes a lot of sense, right? We sent ownership of B on the channel, so we can't use it after that, right? So this is sort of like the very simple idea of how this ownership discipline ensures that there's, if I can mutate through this pointer, then there can't be any other parties that are trying to access the contents of the pointer at the same time. Okay, any questions about that? Good, okay. So, that ownership discipline by itself is, well, it's nice if it worked, yeah. No, because you see, you could have the same thing, right? Could be that this thread, upon receiving it, tried to mutate B, and then this thread is reading it at the same time, so you'd have the same possibility, right? Oops. Yeah, exactly. Yeah, it would be a type error as well, yes. Any use of B after that send, because here we're sending complete ownership to the other thread. So, in fact, yeah, this thread may very well have run and deallocated B by that point. Sure. Any other questions? Okay. Right. So this ownership discipline, simple, works. When it works, that's great, but it's very restrictive, right? It says there can only one party that can use B at all, this pointer at all. It doesn't permit any aliasing. Okay. So the way you get aliasing in Rust is through the mechanism called borrowing, which is basically creating a reference to some object. So I'm going to illustrate this through this example. So at the top we define some vector. Okay, this is some code that sets the first, the first element of the vector, or the second element actually. And then there's some operation here that pushes something on the end of the vector and reads it. Okay. So let's zoom in on what's actually going on in that array access there, that vector access. So the way that this code, if you actually expand, this is just notation in Rust. Okay. What's really going on is there's a call to a function called indexMut, which takes v as an argument. Okay, so when you write v1 equals 4 or v.push of 6, you're really just calling the push function from the vec library onto with passing the v as the self argument. Okay, so it's the first argument of the function. So it's passing in a mutable reference to v. So this is not passing ownership of the vector. It's just passing in what's called a mutable borrow of the vector. Okay. And the argument 1, okay? So what it's getting back is, in this variable inner pointer, it's getting an interior pointer into the first element in the vector. And then it has a separate instruction where it goes and assigns that interior pointer to 4, okay? So suppose that you expanded out the code like this, and now I tried to write something like v.push of 1, right? So I pass this reference to v over here, and then I try to add 1 to the vector. Okay, this should be an error, and it is an error in Rust, because if this could actually cause catastrophic, a complete failure, because when you do v.push of 1, if the vector doesn't have enough space, it'll reallocate the vector in a larger space. So this could basically invalidate the interior pointer, and if you tried to access that interior pointer afterwards, it would just bomb out. Okay, so so you want the type system to check for this, and it does. So it'll give you an error. I'll tell you the error it gives you in a second. But basically, what it'll actually this is the error, right? So it'll say that we temporarily lost ownership of vector v at this point, and it'll actually tell you that you get back ownership of vector v over here after this block. Okay, so you might wonder what is going on here. Okay. Well, basically what's going on is this borrowing mechanism is a way to sort of temporarily give out ownership or lend ownership to a function that you call, and then you get it back. You get back the ownership at some point in the future. And the question then is, how do you know at what point you get it back? So this is done through this mechanism called lifetimes. So the idea with lifetimes is here's the actual type of that indexMut function. So it takes this ampersand mut, that's this mutable reference type, okay? And associated with that mutable reference type is a lifetime alpha, okay? And you see in the result here, we get back, the interior pointer is also a mutable reference, also with the same lifetime alpha, okay? And so what that means is, you give it a reference to a vector which is valid for this lifetime alpha, it'll give you back the interior pointer that's also valid for the same lifetime. And if we look back at the code, right, what happened was we created this lifetime. The way that Rust will actually make this work is it'll create a lifetime alpha corresponding to this scope, right? And then it will ensure that so this borrow is created with that scope. And that means this interior pointer can also be used within that scope. But once that scope is over, the borrow is not active anymore. And so then you would get back, and this thread would know that the lifetime is over, so it knows that it gets back control of v. Okay. So this is all inferred by Rust, right? You don't actually have to worry about this actively when you're writing Rust code. But the point is that Rust will figure out that you actually, when you give out references to things, and it'll figure out when is the soonest time when you can get back complete ownership of them. So that was an example of what's called mutable borrows. Okay, that's when you create you create this alias that can be used mutably. But by itself that wouldn't allow something like this. So here, right, we want to create, in this example, we have 2 threads. that both want to refer to, they both want to have read-only access to some shared variable. Okay, and so this would not be allowed by the ampersand mute, because ampersand mute only creates a mutable reference, and that's the only, when you create a mutable reference, that's the only one that can be used to access the underlying contents. With a shared borrow, you can create multiple references, but each of them can only, at least in the way the type system is usually explained, each of them can only be used to read the variable. So here, ampersand x here will create a shared borrow of x, which is valid during the lifetime of this join operation. And after the join is over, we get full access to x again. We can mutate it. Okay. So the idea is, these shared borrows have the advantage that they can be freely copied. So you can make multiple aliases, but you can't mutate through them directly. Any questions about that so far? All right. So summing up what I've shown you, this is like so far the party line about Rust, is it's based on ownership. There's full ownership, which is very black and white. Then you have the ability to create aliases, which can either be used mutably if they're the only active alias, or or in a read-only way if you have multiple aliases. Okay? And the lifetime mechanism sort of works under the covers to figure out how this is valid. Yeah. How difficult is it? It's based on a sort of set of relatively simple rules, but I mean, so the short answer is I actually don't know the full algorithm, and that's not something we have been focusing on so far. We haven't been actually looking at exactly how it does the inference. We assume we're given a program where the lifetime stuff is explicitly written out, okay, which is basically would be the output of the type checker is something called the MIR, or mid-level intermediate representation in the Rust compiler, and we're sort of studying things from that level down. So it's not trivial, but it's not it's not extremely hard, I think. Okay, good. So where things get really interesting is this idea of interior immutability. So what, so far I have not given any way, I've not described any way to define shared mutable data structures. In other words, data structures that can both be aliased and mutated through those aliases. And the way that Rust supports these kinds of data structures is in a sort of, you could say in an ad hoc basis. So it does it through libraries. So there's, in the Rust standard library, there are a number of data types that have this property called interior immutability, which means that just given a shared reference to such a type, T, you can use the operations that are available to you on these shared references to effectively mutate the underlying object. And because, as I said, this has to be this is not something that's supported by the core kind of typing rules or the typing mechanisms that I've described so far. These libraries are all implemented in Rust using unsafe features like raw pointer accesses where the aliasing is not tracked. And the claim is that these unsafe features are being safely encapsulated, whatever that means. Okay. Well, what it means is, or what it's claimed to mean, is that if a client sticks to the interface of the library and only uses the operations that have been blessed as safe, then they should never encounter any undefined behavior. So let me give you an example of this. So the classic example is mutex. All right. So here we have a mutex being created M. All right. So mutex here is a mutex I32 is an integer that's wrapped in a mutex. So the only way to get access to it is to call the lock operation on the mutex. And what we have in this example is really simple. There's just two threads running in parallel that each try to increment M by first acquiring the lock. This gives you back, all this stuff is, you can ignore the details of this. It basically gives you back access to a mutable reference to the underlying contents, which you can then increment. And then, right, so in this case, we're running these two things in parallel, and the idea is that this should be safe because you have to use a lock to synchronize between these two things, right? So that's the only way to get access to the mutable access to the underlying contents is by first calling this lock function. And notice that once this join is finished, we get back complete control of M again, right? So here we can actually just access the contents without the lock. So to sum up what's going on here, the idea is that a shared reference, one of these shared borrow types, is really establishing a sharing protocol, meaning it's describing what operations are available to the object when it is shared between multiple aliases. So in the case of something, a simple type like I32, the only access that shared borrows give you is read-only access. In the case of a mutex, you actually get read-write access, but only by calling the lock function. Okay? And the point is that for any type, you can effectively have a new sharing protocol. Any questions about that? Okay. So that's my high-level bit about the Rust type system. So the question is, effectively, this type system is kind of extensible because you keep defining the way that you support things like shared mutable data structures is by extending the language with new libraries that use unsafe features. And how do you know that those libraries are safe? Yeah. 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 Well, I mean, before what we're doing, there's no safety defined anywhere. Right. I mean, so we're sort of we have to figure out what safety should mean. Yeah, this is all yes, this is informal. Yeah, I mean, ultimately, we want safety to mean we have some operational semantics for the language, and ultimately, what we want is to say the following: if you write programs that are well typed, meaning they only use the safe features of the language, except for these libraries that have been somehow verified as safe, then your program will never encounter undefined behavior. Okay? Okay. So, on to RustBelt. So the first thing we had to do in this project was to actually define the language, okay? Because Rust doesn't have any definition. And obviously, we didn't start out by trying to define the full language because that would be crazy. So instead, we defined a more core calculus, which we call lambda Rust. And it's basically a CPS-style lambda calculus, which supports low-level memory operations. And I'm not going to show the full language because that's quite involved. I just want to give you a flavor of what the types look like. I would say, okay, so this is some of the key types. I mean, there's things like bool and int. There's own of tau, which is what we call an owned pointer. Okay, so it's a pointer where you own not only the memory location storing the pointer, but also the contents associated with. You also own the contents of the pointer, the thing it's pointing to. We have a mutable borrow type and a shared borrow type, which parallel the mutable and shared reference types in Rust. And then there's product types and sum types and recursive types and other things like that. Okay. We have typing contexts, and the typing contexts here are somewhat different than in other languages you might have seen, because this is a substructural type system. It's an ownership type system, meaning that you have to control for things like duplication of resources and so forth. So the way it actually works is we have gamma, which that's just a variable context. It just says, okay, I have certain variables that are values or whatever, and I have a typing context T, which then assigns types to paths. Okay, we'll see an example of this in a bit. Paths here are just things like x or x dot and some record field. Then there's basically two major typing judgments. There's a bunch of other auxiliary judgments. So this one is typing individual instructions S or commands S, and it's saying basically if you start out in typing context T1 where you own certain the things described in T1, then after S executes, then you get back some value X for the return value, and T2 holds after the command is executed. And then for typing whole functions, there's no post condition because we just do everything in CPS style. Okay, so you have instead an additional context K, which gives you the type of the continuation. And at the end of the function, you call the continuation. So just to give you, I'm not going to go through typing rules in detail, but I just wanted to give you some sense of what they look like. So this is one typing rule, for example, for assignment. Okay, P1 : P2. You assume that P1 has some mutable borrow type, ampersand mut of tau, and that P2 has tau, and then afterwards, what do you learn? Well, actually, you just learned that P1 has mut tau. What happened to P2? Well, it got stored into the location, so you've now lost control of that. Any questions? Here's another one. This is just a let binding. So here you have, right, so if you have a statement S that takes you from typing context T1 to typing context T2, and then starting in typing context T2, you can execute the function F, then you can run the entire let expression in the initial context, T1 combined with whatever T is left over. Yeah, Alex. Yeah. That's been dropped. Well, it's a good question. So Rust is an affine type system. So it allows you to just sort of forget stuff. There's nothing tracking. There's nothing enforcing that you have everything from the context. You're allowed to just forget about things. And the language is set up. The semantics of the language is set up so that most things, when they go out of scope, will run a destructor. But actually, as it happens, the language does not enforce absence of memory leaks, and so we don't have to really worry about that. Yes, but the simple technical explanation is it's an affine type system. You can drop arbitrarily resources on the floor. Okay, so getting to this question of safety. So the standard syntactic approach that people use to proving language safety is the so-called progress and preservation approach. And this is where essentially you define some notion of, you lift the notion of typing to machine states. You say, when is a machine state well typed? And then you say, well, you prove that as long as a machine state is well typed, then any state that it steps to continues to be well typed. And so you always have well-defined behavior. Okay. This theorem is totally useless if you have unsafe code, because the unsafe code is not well typed. So it doesn't tell you how you can, it doesn't say anything about interaction of well-typed code and libraries that use unsafe features. So this is basically a non-starter. So instead, we use this more semantic approach based on what are called logical relations. How many of you have heard of logical relations? Oh, okay. All right, not so many. That's fine. That's actually okay, because as you'll see, they don't look like logical relations in the usual sense. Logical relations are a classic semantic technique, traditionally for like proving normalization of languages or termination for more simply typed languages. And it's also useful for proving things like contextual equivalence. But here we're actually using it as a way of proving semantic safety of the language. And what's unusual about our approach to logical relations is that actually we define them by interpretation into a logic, which is not, despite the name, is not actually the way that they're typically presented. So the high-level idea, and then I'll go into more detail about this in a bit, is that for every type, we're going to define an ownership predicate, which says, effectively, what is the semantics of the type, right? It says, if T is the thread that owns something of type tau, and V bar, which is a sequence of values, is the representation of tau, then this will tell you the predicate that has to hold, okay? Describing the fact that you own this value of type tau. So again, we'll see examples of this in a bit. But that's the high-level idea. It's describing what ownership means at type tau. And then once you have this notion of ownership, the ownership interpretation of types, you can then lift this to context in sort of the obvious way. By the way, oh yeah, something I should have said first. So the fact that I'm talking about ownership in a logic, you may not be surprised that the logic we're using is a separation logic, okay, where the notion of ownership is a sort of built-in concept. How many have heard of separation logic? All right, that's good. I'm not assuming any fancy, I'm not going to assume you know any fancy separation logic, but maybe if you've heard of the basic concept of it, that would help. So yeah, we're relying on a separation logic, and so then the idea with semantic context is that if I have in my context that I own P1 at type tau1 and P2 at type tau2, what that means is simply that I have the ownership predicate of tau1 at P1 and the ownership predicate of tau2 at P2, and they're joined together by the separating conjunction operation from separation logic, which means you can roughly think of it as meaning that, very roughly, that they hold of different pieces of memory. Okay, that's the sort of simple interpretation of separation logic. As I'll explain in a bit, we're actually using something more sophisticated than that. But that corresponds to the intuition. If I have like a variable x, in my environment and a variable y, they actually are pointing to different pieces of memory. And then finally, we can lift this all to a semantic version of the typing judgment, which is just expressed using Hoare logic. Okay, so the idea in kind of the obvious way. All right, I'm eliding some details for purposes of presentation, but not too many really. So the idea is that the meaning of this semantic judgment about a command S is just that if I have some interpretation of the context E and L, oh, I forgot to say what E and L. Not sure if I said what E and L are. They're just contexts that have information about the lifetimes. I'm not going to go into it in detail here. So if I have that information in my precondition, and I have the interpretation of T1, right, the ownership interpretation of the context, then in the postcondition, I get back the ownership reading of T2. Okay, so it's kind of what you'd expect to see. Okay, so now that's the high-level structure of what we end up defining. And then what do we do to actually prove safety? First, we prove what are called compatibility lemmas, and this is a standard technique from the logical relations literature. The idea is that for every syntactic typing rule, so right, these are the syntactic typing rules I wrote before with these single turnstiles, you prove a semantic version where you just replace all the single turnstiles with double turnstiles. In other words, you prove lemmas now, which say, for example, if I have the semantic version of this one and this premise and the semantic version of this premise, that implies the semantic version of the conclusion. Okay, those are the compatibility rules, and then you have. So how does this then give you safety? So first, let's just revisit how you regain sort of normal syntactic type safety. In other words, if your whole program is well typed, doesn't use any unsafe features, this gives you safety because from the compatibility, you know that if your whole program is well typed, then it's also semantically well typed. Okay, according to the semantic typing judgment. And we also have a theorem which we call adequacy, which says if your whole program is semantically well typed, then it's actually safe to execute. So those two things together will give you the sort of standard well-typed programs don't go wrong result. But the more interesting thing is what happens when you link with unsafe code. And there, the semantic safety gives you exactly what you want. So the idea is for well-typed code, we have what we just said on the previous slide, right? That if you have a safe function, then syntactically safe, then it's also semantically safe. If you have a library that uses unsafe features, you have to manually prove that it's semantically safe. But at least now we have a definition of what semantic safety is. So we can prove that semantic safety for the unsafe libraries. And then by compatibility, we can link those unsafe libraries with any of the safe libraries, because they're all we've proven the compatibility for the semantic judgment. So like the end result is that the whole program is safe, so long as the unsafe pieces, right, the pieces that use unsafe code that you've verified manually are safe, are also, as long as you've verified that those are safe. Okay, so that's the end-to-end result. And what we've done in the project so far is we've actually verified this this compatibility rule. We've verified all the compatibility rules for the type system we've written down, and we've also verified. We've done this manual verification of semantic safety for a bunch of these core libraries that use unsafe features, these interior mutable types. Okay, so assuming I have some time left. Huh? 8 minutes? Great, okay. That should be enough to do something. Okay, so I want to go into how we actually define this logical interpretation of types, because this is where we get to the meat. I mean, so far it's all been about, this is sort of just structurally how we set things up. So the big question is, what logic should we use? So I've already suggested why separation logic is a nice fit. It has a built-in notion of ownership, which matches the notion of ownership at the Rust type system. But we also need other things. So we also need the ability to talk about these sharing protocols that I've been somewhat vague about, but I gave you a couple examples of. Also, we need to deal with higher order features of Rust. So we're working in a higher order concurrent setting. So obviously, okay, at least to me, the right choice of a logic for interpreting Rust is higher order concurrent separation logic, which you may or may not be familiar with. But there's actually been a lot of work on this, and this is part of the problem. Even once we've made this obvious choice, there's still the question of which one. Okay, so. In particular, so this is sort of a brief picture of concurrent separation logic research over the past, 15 years or so. Or no, actually, well, it goes back to the 70s up there. But most of this came since Peter O'Hearn developed concurrent separation logic in the early 2000s. And there's been just a huge, there was many years where there was just a paper every year or a couple of papers every year of some new extension of concurrent separation logic. And the reason is because of this stuff with the shared protocols, which ties back into these shared reference types. Basically, the original concurrent separation logic let you talk about, let you establish invariance on shared state. And that's very useful for an impressive range of examples, but ultimately you often want to talk about more interesting kinds of protocols on how the shared state can change over time. And so that led to all these logics with rules like this. Okay, so I expect you to read this very carefully. This, alpha over there, the thing. What? It makes sense. Yeah, it makes sense. Of course. No, yeah, well, for a while I thought it did. So, no, I mean, I contributed that rule. One of the smaller ones, I have to say. No, I'm kidding. So these are some of the more advanced ones involving various higher order features and so forth. And they were getting extremely complicated. And the point was that in all these logics, these super complicated and obviously not terribly canonical rules were being built in as primitive, and their soundness proven directly against some rather complicated model. So this brings me to the logic we're going to use, which is, of course, the one that we developed, which is called Iris. So Iris is another project that we started a couple years ago, I guess in 2014. Originally, the goal of Iris was just to sort of, well, actually, it came out of trying to write a book about not about concurrent separation logic, it was about logical relations. But we realized we didn't know what was the right logic to use, and we didn't like any of the existing ones, they were too complicated, so we tried to come up with something that was simpler. Basically, the distinguishing features of Iris are, it has a very simple foundation. So it's just higher order BI. BI is basically the assertion language of separation logic, plus a handful of modalities. And these are mostly pretty well understood modalities. They're things like there's a box, which is a comonad, and there's an update modality, which is just a simple monad. I'm not going to go into the details of that here, but you'll have to believe me. You can look at our ESOP paper from earlier this year, which shows the details of that. So once you have this simple foundation, then the whole idea is that you can derive a lot of those super complicated rules in the previous slide as just modes of use of these of this simple set of features. And those rules are all those logics are kind of derivable within Iris. It also supports imperative invariance. I'm not going to talk about that. And lastly, in the last year and a half, Robert Krebers, who joined the project about 2 years ago, developed extremely useful tactical support for mechanizing proofs done within Iris in the Coq proof assistant. So I think Iris is a very perfect fit for modeling Rust. I'll just show you quickly a little bit of something interesting about the ownership interpretation, the way that we use Iris. So here's, I have like 2 minutes. Yeah. Oh, 4. Okay, great. So here's some very simple types, right, which have the obvious thing. So the interpretation of bool is that V is a bool if it's either true or false. Okay, so that's pretty clear. Okay. Product types, right? You have a sequence of values, V, that can be split into the first part of the sequence and the second part of the sequence, V1, V2. So the sequence represents tau 1 cross tau 2 if the first part represents tau 1 and the second part represents tau 2, because we're assuming the products are laid out in memory sequentially, the first part and then the second part. Where things get more interesting is with pointer types. How do you interpret pointer types? So for these own pointers, if I have what represents an own pointer is a single location, right? So that's the inhabitant of an own pointer is just a memory location, L, together with two things. One, ownership of that memory location. So this points to connected from separation logic. L points to some value W bar, or some sequence of values W bar, together with ownership of the underlying, the contents of the pointer, the tau, okay? So that's why you have both the ownership of L star the ownership of tau. Ignore this modality for a minute. I can explain that later if anyone wants to know more details about it. Where things get really interesting then is with mutable borrows. So at first glance, the interpretation of these mutable borrows looks exactly the same as the fully owned pointers. Can anyone spot the difference? There's an ampersand in there. Yeah, what's this thing? Okay, well, I should have had a point over there. Right. So Yeah, so it's almost exactly the same, except there's an ampersand kappa in front of it. Okay, so indeed, this is not like this is not sort of good old-fashioned, grandma's separation logic from the year 2000. This is a new thing that we had to develop to make sense of what these mutable borrows are doing, and it's basically an abstract predicate in a logic which we call lifetime logic, which is one of these custom logics that's derived within the Iris framework. And I'll just give you the very high-level story here, and then I'll wrap up. So. The very high-level story, which I think is very interesting, is that traditionally, right, the way that you read separating conjunction in separation logic is you say P star Q means I own a piece of memory that satisfies P, and I own a disjoint piece of memory that satisfies Q. Right, so they're separated. The two pieces of memory are separated in space. With borrows, you need something. You need a notion of splitting as well, but it's one that should be separated in time. So the idea is that if I own some resource described by the proposition P, then I want to be able to borrow it, or to create a mutable borrow of that for some lifetime kappa. And the idea is that this assertion is going to mean I can, if I own that, then I know that I can get access to the underlying P whenever I want, as long as the lifetime kappa is alive. It's still ongoing. Once the lifetime kappa is dead, the original owner of P should be able to get back control of it, and that's what is indicated by this, what's called an update, a ghost update in Iris. So the idea is this funny symbol here, this dagger kappa, means kappa is dead. Okay, this is knowledge that kappa is dead. So if I know that kappa is dead, I can use that to get back ownership of the original resource. Okay, and the point is these two things are separated by star. So once I've created this borrow kappa of P, I can give that to one party, say the function that I'm calling. And I can keep for myself this other one. So I know once I've established that kappa is dead, I can get back the P. And I don't have to worry about any communication or synchronization between the party that has the borrow and the party that has the, oops, sorry, there was actually an animation here. The party that has, what we call the inheritance, right? The ability to get back P once kappa is dead. And so the ability to support this kind of non-standard interpretation of ownership and separation is exactly what a lot of the work on concurrent separation logic, and in particular Iris, has been trying to do. I'd love to tell you more about how we actually do that, but that's a much longer talk. So I have to wrap up, right? Yeah, okay. I'm gonna wrap up. So there's a lot more details in the paper about the type system, this lifetime logic, how this actually works, how you can use this lifetime logic to model a bunch of these types, these Rust types that use interior immutability. And there's a lot of stuff about lifetime, the notion of lifetime inclusion and subtyping, which I haven't talked about at all, but which is pretty fundamental to the Rust type system. Things that are still missing from the language, from RustBelt, there's a lot of things. The biggest one that we're focused on actually is weak memory. So I haven't said anything about this, but we've been assuming in this work sequential consistency. And we're very interested as part of a bunch of related projects we've been doing in expanding our RustBelt model to handle weak memory, because several of these the real implementations of these libraries actually use weak memory primitives of LLVM. And then there's several other features of the language that are quite interesting, which we haven't modeled, like trade objects and panics. So the conclusion is basically logical relations, especially logical relations interpreted into a separation logic, are a great way to prove safety of a real language. In a way that's actually extensible, where you can actually extend your soundness proof to handle new libraries as they're developed, even if those libraries use unsafe features. And these kind of advances in separation logic that have come about in the past 15 years, where you have the ability to talk about non-standard interpretations of separation and ownership, are what make this possible. Thanks.
Thank you. Okay, questions? Yeah, Alex?
Maybe I can bother you some more about the affine types. So I remember seeing some talks about Rust a while back, and the fact that the memory management is kind of also done for you is another marketing point. So, I mean, is there some subset of Rust for which it's guaranteed that you don't get memory leaks?
Not that I know of. So this was actually the source of one of the most infamous Rust bugs, was that it kind of gives you absence of memory leaks most of the time, but not all the time. And there's ways of, I mean, basically, because of the existence of certain libraries, like the RC library, the reference counting library, it's not easy to banish memory leaks, and they didn't want to give up those libraries just to get the full result about this. But yeah, there was sort of an assumption, because mostly you don't have memory leaks, that assumption somehow made it into the implementation of one of these libraries. In fact, it was a library that's very similar to this join construct that I was showing earlier. It's called scoped threads. And they sort of had this assumption that the destructor is eventually run, and that's not actually the case.
Great, thanks.
Other questions? Yeah.
So you said you tried to prove something like RustBelt and mutex to be safe. Did you find any cases where this was not possible, and do you have an example of this, like cases in which it was unsafe?
Oh, you mean did we have a negative, or did we find a bug?
Yeah, exactly.
We found a bug, but it wasn't. I mean, it's sort of not too exciting, but it was a bug. I mean, there was a soundness bug in. It wasn't in the library itself. It was actually in. I'm forgetting now. I think it was in mutex guard. So something I didn't talk about at all, but it's on the slides here actually if you want to look at it, is this idea of thread safety of type. So there's this notion in Rust of send and sync traits which describe when it's safe to transfer ownership of an object from one thread to another. For certain types that's not safe, like RC for example. There's when you define these unsafe types, you're supposed to also put in rules about when they're safe to send or not. Otherwise, it automatically figures out, it automatically infers some rules, and I think it had automatically inferred some rule which was wrong, and so yeah, you could dump core using that. But it was a good example of something that we only found. Ralph, my student, only found as part of doing the verification. We had to write out what are all the rules because we had to actually verify that those rules about the send traits were sound. And then he looked at and looked at it and saw that there was this errant rule.
So maybe a follow-up question on that. Have you already verified some unsafe code against those rules?
Well, yeah. I mean, it's all in Lambda Rust, right? So this is not. We're not verifying the existing the Rust implementation as it is. But yeah, we have basically ports of all these ones I listed here. Here, yeah, we have ports of all these and a few others. Into Lambda Rust. I mean, these are fairly, this is sort of an ideal case for this kind of verification technique because these are relatively simple code. I mean, there's not many lines of code. They're doing fairly simple things. What's tricky about them is the types that the library is giving to these operations.
Right.
And so it's kind of the sweet spot. The place where Iris really buys you a lot is when you have very complicated reasoning about very small code. If you have some longer libraries, then you would want to have more automation to handle the sort of tedious stuff. But basically, in the kinds of things we've been verifying, there's almost no tedious stuff. It's almost all just hard math.
Okay, so thank you for your talk.
Sure.